Hello, am I audible?
Yeah, now
Yes,
you are.
Okay. And can you see my screen?
yes,
Yes.
Okay. So previous session we discussed precision and recall, and now we will see two examples where in one example we want high precision and in another example we want high recall, right? Yes. So suppose if we want to build a model to predict whether the given video is safe for kids or not, right? So for that, let's say if we want to uh, build a machine learning model and model given any video, model will predict whether the given video is safe for kids. So in this type of application, we want high precision, right? Because if model is predicting that that video is safe for kids, it has to be actually safe for the kids, right? So given these video, let's say if model is not able to uh, select this positive part, this true video model is not able to capture, then also it's fine because here model is saying this fourth video is safe and sixth video is safe, right? So when model is saying these videos are safe, they are actually safe for kids, right? So in this case, we want high precision, right? But some positive cases, some safe video, this model will not capture, right? Because we when we have high precision, then recall will be low, right? Yes. So in high precision, we are okay if model is not able to classify some video. So example here, this video number 2 as safe for kids, but whichever video model classify as safe for kids, they are actually safe, right? So this is the application where we want high precision. Okay, yes. So we would prefer model which has high precision, and since model has high precision, recall will be low, right? And it is okay if model reject many good video, but keep only really the safe one, right? The second use case is, let's say we want to build a model which detect shoplifter on the basis of surveillance image, and if there is some positive detection, then it will be also examined manually, right? So first we will detect, and then if any positive detection is found, then we will manually examine it, right? Now in this application, we want high recall, right? Because we don't want to miss any positive case, right? We don't want to miss any shoplifting cases, right? So here we would prefer model to have a high recall even if precision is low, right? Because here our goal is to catch almost all shoplifter cases, right? So for that we want high recall, right? So here high recall means it may possible that model is saying this is the true positive case, this is the true positive uh, example, but the model prediction is wrong, right? Because if recall is high, then precision will be low, right? So in high recall, our system might catch some non-positive case, some non-shoplifter cases, but here we want to, our goal is to capture all shoplifter cases, right? So here our requirement is to achieve high recall, right? And since we are achieving high recall, then precision will be low, right? So here two cases are there, right? So this is the true, this is the positive case. This is again the positive case, right? But since our recall is high, so it may possible that uh, this case, this third case, our model also predict as a shoplifter case. But since this case, this example is not positive, right? So model is here predicting false, right? Okay, but since we are having high recall, so therefore model will try to capture all shoplifter cases, right? Okay, so any doubt in these two examples? Okay. Now we will see one more performance matrix, ROC curve. So mainly we will use accuracy, and if data set is biased or we are having classes in majority and minority, then we will use confusion matrix, precision, recall, F1 score, right? Especially F1 score we will use when we want to give equal weightage to both precision and recall, right? So precision is also important, recall is also important, then we will consider F1 score. ROC curve we will use when we have to select one best model. So suppose we are having multiple models and we want to pick one best model, then we will use ROC curve, right? But yes, accuracy we can also use. So for example, let's say if there are 10 models, so let's say model 2 is giving the highest accuracy, then we can also decide on the basis of accuracy, on the basis of precision, on the basis of recall also we can decide the best model, right? So it depends on what type of problem we are solving, right? What is our goal? And on the basis of that, we will decide we will select the best performing model, right? Okay, so ROC curve is nothing but the receiver operating characteristic curve, right? So here, as I said, this ROC curve is helpful in comparing performance of different models, and we can choose best model using ROC curves, right? So here we will see ROC curve of two different models, HGT classifier and random forest classifier. So again, this HGT classifier we are doing here for classification task, and random forest classifier also we are doing classification, right? And in ROC curve, we will use area under the curve, right? So here, let me discuss these ROC curve. So here, x-axis we will have false positive rate. So false positive rate and y-axis we are having true positive rate, right? So false positive rate is nothing but the uh, yes. So false positive rate tells us what proportion of patient that were actually not having cancer are classified as having cancer, right? So here, false positive rate is nothing but the ratio of yes and divided by total number of cases. So say 10 divided by 50 plus 10, which is nothing but the false positive divided by true negative plus false positive, right? And true positive rate is nothing but the recall, right? Okay, so we will calculate these two ratio, false positive rate and true positive rate, and then for different value of threshold, we will plot these values, right? Okay, so after plotting these values, false positive rate and true positive rate for different values of threshold, we will get this curve, AUC curve, ROC curve, right? After getting this ROC curve, we can calculate area under the curve, right? So suppose this is the ROC curve, then we can calculate here area under curve, right? So here this area under curve is, let's say, 0.4. So this number will tell us how good our model is, right? So if AUC is zero point 0.4 and let's say here AUC is 0.9, which means since here we are getting higher AUC, which means this is the best model among all these four models, right? Yes. So ROC curve we will plot false positive rate and true positive rate, right? Just like we did for the precision recall curve, right? In precision recall also, we are changing this threshold and we are plotting different values of precision and recall, right? Yes. So in ROC curve, we will use false positive rate and true positive rate, and we will plot this curve, right? And then we will calculate area under the curve. Okay. So in this case, suppose we are using random classifier. So for digit 5 prediction, right? So 50% of time, let's say we are predicting digit 5. Remaining 50% of time, we are predicting not 5, right? So if you calculate here AUC area under curve, you will get zero point 0.5 value, right? Because 50% of time, since we are predicting 5 and 50% time we are predicting not 5, so false positive rate and true positive rate, we will get 0.5, 0.5. So that's why we are getting here y is equal to x, right? And if you calculate here area under the curve, so complete area is 1. If this complete area is 1, and since here we are only considering half area, so therefore ASC is 0.5, right? Okay. And if let's say if we are suppose our ROC curve is something like this, so here we will get area greater than 0.5, right? So 0.7 here is the area. If you let's say if you have ROC curve, let's say this fourth case, now AOC is 0.9. So if you have to select the model out of these four model, you would select this last model, right? Because here in this case we are getting uh, highest AUC area under the curve, right? Any doubt here? Hello, am I audible?
Yes.
Yeah.
Okay. Yes. Okay. So let's take another example for five detector. In five detector model, what we are doing, we are detecting handwritten digit 5, right? So 5 versus not 5, we are detecting using this 5 detector model, right? So I have already discussed this 5 detector model, and we build this model using SGT, right? Okay. So if you implement this 5 detector model, which is nothing but a binary classification model, which detects digit 5 versus not 5 cases. Uh, and let's say in one case you are using HGT classifier, in another case you are using random forest classifier. So we are having two types of classifier, right? And let's say if you plot ROC curve for both classifier HGT and random forest. So this is the curve for random forest and sorry HGT, and this curve is a curve for random forest, right? So clearly here, if you calculate area under curve, you will get high value or high area when you use the random forest classifier, right? So here, on the basis of this ROC curve, we can say that this random forest is doing better than the SGT classifier, right? Okay. Yes, but to draw this ROC curve, we have to calculate false positive rate and the true positive rate, right? So here the true positive rate is nothing but the recall, right? So true positive rate is same as the recall. So which is nothing but the false positive divided by false positive plus true negative, right? Similarly, this false positive rate is the ratio of false positive divided by false positive plus true negative, right? So here, if you calculate the false positive rate for this example, you will get value 10 divided by 50 plus 10, 10 divided by 60, right? Which is nothing but the, here we are calculating what proportion of patient uh, that actually were not having the cancer are classified as having cancer by our model, right? Because this side we are taking model prediction, this side we are having actual prediction, right? So this is the false case, right? The false actually actual false or false case we have for this particular row, right? Because in this row we are having no cancer, right? So out of these cases, these 60 cases where actually we don't have any cancer, 10 times model is predicting cancer, right? So this ratio is called the false positive rate, right? Okay. So far we have discussed 5 detector, which is nothing but a binary classifier, right? So using this 5 detector, we are predicting digit 5 versus not 5, right? Now we will see the original problem where we are given digits, handwritten digits from 0 to 9, and we have to predict 10 categories, 10 classes, right? So now we are solving a multi-class problem, right? In multi-class problem, we are having multiple classes and output is one out of given classes. So suppose if there are 10 classes, in output we will predict one class, right? Yes. So again, for the multi-class classification problem, we are using SGT classifier, right? So SGT classifier we can use to solve binary classification problem. We can use to solve multi-class classification problem, right? And in fact, for regression also we can use this classifier. Yes, yes. So here we will first create instance of SGT classifier, SGT underscore CLF, and then we will fit our data to this model, right? So X train is nothing but the training data, and Y underscore train is the output labels, corresponding output labels, right? Okay, so using this fit function, we can fit SGT classifier for our data, right? And then if you want to predict for any given image, you can do using this predict function, right? So SGT underscore CLF, which is nothing but your model dot predict, and here we will pass input, right? So for this given input, it will predict its class, right? And since there can be total 10 classes, so in output we will get either 0, 1, 2, 3, or 9, depending upon its class, right? Okay. And here also we can use cross validation to select the best model, right? So SGT underscore CLF is here. You will pass our model, and then you will pass training data. Then you will pass the corresponding output label. And here we will mention, let's say, if we want threefold cross validation or fivefold cross validation. So accordingly, we will pass here some number. So for example, if we want threefold cross validation, we will write here 3, and here we will pass scoring criteria. So on what basis we want best model? So we want to get the best model on the basis of accuracy. So here we will write accuracy, right? So it will perform threefold cross validation, and it will return the model on the basis of best model on the basis of highest accuracy, right? Okay. Now, in this case, we can also use feature scaling, right? So, if we want to use feature scaling, then I already discussed two techniques for doing feature scaling. We can use min-max scaling or standard scaling. We can use, or we can normalize our data, right? So let's say if we want to use standard scalar, then we will import standard scalar from package scikit-learn preprocessing, and then we will fit our data so that we can do feature scaling for the given data, right? So here x underscore train is the input data, and here we are first using the feature scaling. We are doing the feature scaling, and then after scaling features, we will select best model using threefold cross validation, where we are using accuracy as the selection criteria to select the best model, right? Okay,
Dr.
so in
Praveen,
this, yes.
1 second. So the standard scalar, min-max scaling that we
Mhm,
are using in order to scale it to one scale, right?
mhm,
Everything. But here we have only digits from 0 to 9. What is
mhm.
that we are going to scale here?
Yes, yes. So it will convert each pixel value in 0 to 1 range, right? So here in since we are dealing with the images, so each pixel is a feature, right? So for example, let's say if we are having 7 by 7 image, if we are having 7 by 7 image where 7 is the width and 7 is the height, then each image or each input will contain 7 into 7, 49 features, right? And
Okay.
yes, and after doing this feature scaling, it will convert each pixel in range of 0 to 1, right?
Okay.
Yes. So we can using HDD classifier, we can do the binary classification, we can do the multi-class classification, right? Yes. So here in both binary classification and multi-class classification, uh, for each input, we will predict exactly one class, right? The only difference is in case of binary classification, we are only having two classes. In multi-class classification problem, we are having multiple more than two classes, right? But in output, for each input, we will predict exactly one class, right? Now we will see other types of classification, multi-level classification, multi-output classification, where for the same input, we will predict multiple labels. For the same input, we will predict multiple classes, right? So here in both binary and multi-class classification, output class will be exactly one, right? In binary, we are predicting one out of two classes. In multi-class classification problem, we are selecting one out of capital C classes, right?
What is the difference between multi-label and multi-output?
Yes, yes. So I'm multi-label and multi-output are the related. The very small difference is there. So in multi-label, okay. So I'm coming to that point, right?
Okay.
Okay. So suppose let's say if you want to label a email, now the email you can assign multiple labels, right? So same email you can assign important label, then you can also assign let's say um, uh, academic, right? So suppose email is related to some academic part, so academic also you can, so for the same email you can assign multiple labels, right? So the tagging problem where we are tagging email is a multi-label problem, right? Because for the same email we can apply multiple tag. Similarly, here if you this movie, let's say, so here also we can assign multiple labels, right? So let's say this here you can assign biography is true, drama is true, sport is true, and let's say the science fiction is false, right? So multiple classes or multiple labels you can assign here for the same input, right? Now, uh, for a given input, there can be more than one classes present in the same input, right? So it may possible that for some input only one class is there, sport is there, or let's say only drama is there, or let's say drama and sports both are there, right? Or let's say, uh, for example, here these three classes are present, right? So this type of problem is called multi-label classification problem, right? Where for the same input we may have multiple labels, multiple classes are there for the same input. Okay, so here in okay, and let's say this is the second input. Again, we are having there can be multiple labels for the same input. So let's say for this input we are having drama as a class, right? So the important point here is for the same input we may have multiple classes, multiple labels as a output, right? So here classes means labels, right? Okay. So this type of classification is called multi-label classification, and in multi-label, these categories or these classes uh, are binary type, right? So, for example, input can be can belongs to sport or may belongs to sport, may not belongs to sport. So here we can only have two values, binary values we can have for each class, right? So for sport, we can have zero value, we can have one value. So only two possibilities or two options are there, right? Or in other word, each class here we are having binary values. So if we are only having binary values for each classes, each categories, then that problem is called multi-label. If here we are having multiple categories, then that problem is called multi-output classification, right? So in multi-output and multi-labels, in both cases, we are having multiple outputs or multiple labels multiple labels are present for the same input. The only difference is in multi-label, in each category we can have we can only have two values, right? If we are having more than two values, then that classification is called multi, right? Okay, so clearly here for this problem, we since we are only having two values in each classes, right? So for example, this movie can be drama or may not be comes under this category, right? So only two values are possible here, one or zero, right? So so since only two values are possible for each categories, so therefore this problem is a multi-label classification, right? This is another example of multi-label classification where we are building a model to classify an image into two categories, two labels, right? First label is greater than or equal to 7. Second label is odd. So for the given image, we want to predict these two categories, right? Greater than 7 or equal to 7, greater than or equal to 7, and the second category is odd, right? So let's say for this given handwritten 5-digit image, greater than or equal to 7, this condition is false, and the second condition is odd, yes. So since 5 is a odd number, so this condition is true. So here our classifier output or our model output will be false comma true, right? Because this first answer is false and the second is true, so false comma true it will give, right? Now here for each input we are having uh, we are having multiple outputs, so therefore this multiple labels, so therefore this problem is multi-label classification. And for each categories, we can only have two values, right? True or false. So therefore, this is a multi-label classification problem, right? Any doubt here?
Mm.
Okay. Now in multi-label or multi-output, the pipeline is same. We will split our data, then we will use training data to train our model, and we will use test data to test its performance, right? Okay. So here, what we will do, we will first create output labels, right? Sorry. Okay. So here, the important point is for each input, we will have multiple output labels, right? Yes. So suppose if we want to build a model to classify a given image into these two classes, so first we have to create output label for these two categories, right? So first category or first label is greater than or equal to 7. The second category is odd, right? Okay. So for the given output, because here in the original data set, what we have? We have images and the corresponding label. So we are given handwritten digit images and the corresponding label. So for example, for 0 handwritten digit image, we will have 0 output label. For 5 handwritten digit image, we will have 5 as the output label. So we will create these two labels first, right? Okay. So here we will pass output label, and if output label is greater than or equal to 7, then this condition will be true, else this condition will be false, right? Because our first label is greater than or equal to 7, right? Okay. Now this y underscore train is not a scalar. Y underscore train is a vector, right? So suppose if we are having 50,000 in 50,000 data points in our data, then the size of y underscore train will be a 50,000 column vector, right? And since we are doing this operation where one side we are having column vector, other side we are having a scalar, so it will perform this operation element wise, right? So one by one, it will pick element from this vector and it will perform this comparison, right? So after doing this comparison, we will finally get the vector of true and false, right? If output label is greater than 7, the label will be true, else the label will be the false, right? Okay. So this is our the uh, first label y underscore train underscore large. Now we will create second label. In second label, we are uh, here calculating whether this digit handwritten digit is odd or not, right? So this condition is true or false. We are calculating. For that, we will calculate if output label is divisible by 2, and divisible by 2 means the number is even, right? And if let's say after dividing 2, we are getting remainder 1, then the digit is odd, right? So if digit is odd, then when we divide that number by 2, we will get 1 in the remainder, right? So if we are getting 1 in the remainder, which means the given digit is a odd digit. If this condition is false, which means digit is even, right? So this way we can create two vectors, two column vectors for each label, right? So because here we are having two labels, first label and the second label. So we will create one vector, one output vector for first label, one output vector for the second label, right? And what will be there in these vectors? Vectors of true and false, right? If this condition is true, then we will have true value there. If this condition is false, then we will have false value there, right? So two vectors of true and false values we are creating here. So now for each input, for each image, we are having multiple outputs, multiple labels, right? First label and the second label. Okay. So now what we will do, we will concatenate these two output vectors, right? So for that, we will use NumPy dot c underscore. So NumPy dot NumPy NP is the short form for NumPy, right? So here we are using NP because NP we have already defined as a short form for NumPy array, right? So this NP dot c underscore will concatenate two columns, two array, right? Y underscore train underscore large is the column vector, first column vector of size, let's say 50,000 cross 1, right? Because if we are having 50,000 training data point, then the size of this first vector will be 50,000 cross 1. Size of second vector will be 50,000 cross 1, right? And np.c underscore will concatenate these two array element wise, right? So for example, in first row, we will have first output label, then the second output label for the same image, right? So this way it will concatenate, right? So after concatenating, we will have, let's say, output label 1, then output label 2. So for the first image or first input, we will have these values, right? For the second input, 1, 2. For the second input, we will have output label 1 and output label 2. So likewise, it will arrange all inputs, right? So it will concatenate this first column vector and the second column vector, and finally you will get uh, this type of output labels, right? Concatenated output label. Now we will use this output label and input to train machine learning model, right? Okay. So for that, we will use a multi-level classifier, multi-level classification model. So here you can use any multi-level classification model. So, but here we let's say I'm using k nearest neighbor classifier, right? So k nearest neighbor classifier supports multi-level classification, right? So here again the pipeline is same. We will create training set, testing set. We will build machine learning model using training data, and then we will test test data. We will evaluate performance of machine learning model, right? Okay. So for k-nearest neighbor classifier, we are importing k-nearest classifier from scikit-learn dot neighbor. We are importing k-nearest classifier, and then we are fitting our data to this k-nearest classifier, right? Here we have created one instance of k-nearest classifier, and then for our data we are fitting k-nearest classifier model, right? So in first argument we are passing input data, x underscore train input images we are passing, and y underscore multi-label is nothing but this concatenated vector, right? Because we have concatenated these two output labels, right? So y underscore multi-label is the concatenated output labels, right? Okay. So it will train a k-nearest neighbor classifier to our data, and then using this model we can make any predictions, right? So for example, given this model and given this image, we can use predict method to predict multi-label output, right? So for example, let's say for this image, the first label is false and the second label is true, right? So for example, let's say this is the handwritten digit 5 image, then 5 is not greater than or equal to 7, so condition is false, and 5 is is odd, condition is true. So therefore, we will have false, comma true in the output, right?
How was the k nearest neighbor and all working? So it's just like we just have to call this.
Mhm. So in k nearest neighbor, what exactly this algorithm will do? It will create, it will search for k nearest neighbor, right? So since here we are not, so this k nearest neighbor classifier uh, has some hyperparameters. So number of neighbor, let's say, is a hyperparameter here. So that hyperparameter we can also change. So for example, if that hyperparameter value is 3, it will search 3 nearest neighbor, right? So let's say here we are using 5 nearest neighbor. So in 5 nearest neighbor, it will use 5 nearest neighbor, and using these 5 nearest neighbor, it will decide, right?
So where are we passing this hyperparameter? I could not see any hyperparameter.
No. So but it will take the default value, because we are not passing any hyperparameter value here. So it will take the default value. But yes, that hyperparameter also we can change, right? Okay. So here, let's say if you are using 3 nearest neighbor, and suppose this is this is your input point, right? And for this input point, what it will do, it will search for 3 nearest neighbor examples, right? Suppose there are some more training data is there, but it will only search 3 nearest neighbor, right? So for this given input point, as you can see here, these 3 are the nearest neighbor, right? Now it will calculate, and how this algorithm is deciding that these 3 are the nearest neighbor. It will compute the distance, right? So now you can also change the distance matrix. So but assume here you're calculating Euclidean distances. So on the basis of Euclidean distances, since these 3 points uh, are are the nearest neighbor to this point, so now we will predict output level using these 3 input data points, right? Now to predict this output, again we can have several policies. So for example, we can use voting, we can use the averaging, right? So assume, let's say, if you are taking voting scheme. So in this particular case, let's say we are having two labels. So for example, for this input we are having 2 labels, first label and the second label, right? Here also we are, for this point we are having 2 labels, and for this point also we are having 2 labels. And if you are if you are using here voting rule, so it will check for this first label, first label, and suppose here you are having true, and this case false. So if you consider the majority is 2 time true, 1 time false. So for this input, it will take first output as a true, because true we are having in majority, right? Now assume for this first nearest neighbor, the second label is false. Here also we are having second label is true, second label is false. So now the second label, false, and true, false, we are having in majority. So here it will output false. So this is the working of k nearest neighbor, right? So on the basis of nearest neighbor, it will predict output. And this k nearest neighbor we can use for the classification. We can also use for the regression, right?
So how are we, like you said about points, that this I understood. But in the case of this handwritten digits, that
Mhm.
that is a 786 vector, right? How are we going to plot it like this points?
No. So we can create we can calculate distance between 2 images, right? Because now we are thinking images, each input is a vector, right? So,
Yeah.
yeah. So for example, let's say for 7x7 image, we have converted the 7x7 image to a vector of size 49x1, right? Because we have flattened this image. So now we are having, for each input, we are having this vector. And we can calculate distance between two vectors, right?
Yeah.
Yes. Multi-output classification. So multi-output classification is simply a generalization of multi-label classification, where each label can be multi-class, right? That is, it can have more than two possible values, right? In multi-label, we can only have two values for each label. So for example, here for the first label, we can either have true value or false value. For the second label also, we can have the two values. If we are having more than two values for these labels, then that problem is called multi-class, multi-output classification. So multi-output is simply a generalization of multi-label classification, where each label can be multi-class, can be uh, can have more than two values, right? Now, the example here is removing noise from image, right? So removing noise from image is a example where we are solving a multi-output classification problem, right? In regression also, we can have multi-output uh, problem, right? So let's say for the same input, if we are predicting height of a person and the weight of a person, right? So for the given person, we are predicting two values, height and weight. Then this regression problem is a multi-output regression problem, because we are predicting multiple outputs, right? Similarly, in classification also, we can have multi-output classification problem, and this is one example, removing noise from images, right? Now, let's say for this given image, given noisy image, model will clean this image and it will output clean image uh, as a output, right? So here we will build a machine learning model that will remove noise from input images. So it will take noisy images as an input, and an output it will produce clean images, right? Okay. So here, let's say we are using handwritten digit from MNIST data set, and size is 28 by 28, right? So there will be 28 into 28 number of pixel or number of features in each image, right? So now, can you tell me here the number of output for this problem? Because we are doing multi-output classification, right? So can you tell me the number of outputs that we have in this classification problem? So here we will have 784 outputs, 784 labels, right? Because for each pixel value, we will have one output, right? So for example, this pixel value, we are having one output, right? The second pixel value, we are having second output, right? Because for this given image, in output, what we are having a cleaned image, right? So assume this the size of this image is, let's say, 7 by 7. So there will be total 49 feature in this image. There will be 49 pixel. In output also, we will have a 49 pixels, 49 um, uh, pixel values, right? So since we are having 49 outputs in the output, so in this case there will be total 49 outputs, right? But since here we are having 32 by 32 image, so there will be total 784 pixel values or 784 outputs, right? So in this problem, there will be 784 outputs, right? Now for each output, we can have values from 0 to 255, right? Each pixel can take value from 0 to 255. So therefore, this problem is a multi-output problem, because for each output we are having here more than two values, more than two values are, since we are having for each output. So therefore, this problem is a multi-output classification problem. Any doubt in this example? Is it clear here why are we having 784 outputs? Because for each pixels we are having corresponding output in the output image, right? So if this the size of this input image is, let's say 32 by 32, the size of output image will also be the same as 32 by 32, right? So if there are 784 features in input image, in output image also we will have 784 features or 784 pixel values. So there will be total 784 outputs in this output image, right? And each output we are having more than two values, because we are having 0 to 255 values for each pixel. So therefore, this problem is a multi-output classification, right? Yes. So as you can see here, if we are having 28 by 28 image, then there will be total 28 rows and 28 columns in that image. And for each pixel value, we can have value from 0 to 255, right? Okay. So now we will train a classifier to remove noise from input images, right? So here we are first creating a data set where we are adding noise, right? Noise, because we are having clean images. We are having clean images. So first we will create noisy images, and then we will use noisy images, and we will train a model using which we can remove noise present in the data, right? So here, since we have the clean data set, we have clean images. So here we are synthetically we are creating noisy images, right? So for that, here we are importing random function RND. So NumPy dot random, we import this importing is RND, and then we are generating random numbers, right? From 0 to 100 range, and how many random numbers we want? The number of data points that we have. So len in bracket x underscore train will give you the number of training data points. So for example, if there are 50,000 training data points, this number will be 50,000, right? Because it is calculating the number of rows, number of because len underscore x underscore train will calculate the number of rows. So you will get the number of data points that we have in our data set, right? First is x train, and the second is this noise matrix with these noise values, right? So assume if we are having 50,000 data points in our data set, so there will be total 50,000 rows, right? Up to 50,000. Similarly, here, since we are having 50,000 data points, so there will be 50,000 rows, right? And in each input image, we are having total 784 features. So there will be 784 columns, right? First column, second column, and 784th column. Similarly, here also we are having first column, second column, and 784, right? So first we will create this matrix having random values, random numbers, and we will add these random numbers to our data set to create noisy images, right? So after adding, we will get a noisy image. So now this x underscore train underscore mode is nothing but the modified training data or noisy training data, right? Now using this modified data, this noisy data, we will train a machine learning model using which we can remove noise present in the data, right? Yes. Similarly, we will create a test data, right? Because in test data also we are having clean images. So using the same method, we will create modified test data or noisy test data. Right? Okay. Now, in this case, can you tell me the ground truth or the output label? What are the output labels in if you solve this this multi-output classification problem? So inputs are nothing but these noisy images, right? So training data we will create inputs, test data we will create inputs, right? So by adding this matrix of random numbers, we are creating training input data, and similarly we are creating testing input data. Now, since we are doing supervised learning, what we want? We want corresponding ground truth. We want corresponding labels, right? Now, in this problem, what will be the corresponding output labels? What is the ground truth here? So here, what we are doing in output?
Values from 0 to 255.
Yes, yes. So since here we are cleaning a noisy image, so output is nothing but a cleaned image, right? So this is the output. So ground truth is also will also be a cleaned image, right? Which means the original images, original cleaned images are nothing but the ground truth in this case, right? Because here what we want to build a model that can denoise, that can remove noise present in this input image, right? So for that, first we must have noisy images. So we have created noisy images, right? That our model will take as a inputs, right? Now we also want actual outputs, actual ground truth we want, right? So ground truth in this case is nothing but the clean images, right? So clean images we already have. So clean images are here nothing but the ground truth output labels that we will use to train these machine learning models, right? Okay. So modified X train and modified Y train, here we are creating after adding random values to our input data, so that now we have noisy inputs in for the training part and noisy input for the test part, right? So X underscore train underscore mode is the uh, uh, this is a matrix where we are having input images, noisy input images for the training part, right? Similarly, X underscore test underscore mode is a matrix where we are having noisy test images for the input, right? And for the output, y, because in our notation, x we will use for the input and y we will use for the output, right? So this x means testing input and x underscore train means training input, right? So x underscore train input, x underscore test input, y underscore test means training output, y underscore test means testing output, right? Okay. So in this case, since in output we want clean images, so clean image here is our the ground truth, right? So for that, here what we are doing for training images, for the training output will be the clean image, right? X train is here the output for training part, and x underscore test here is the output for the test part, right? Okay. Now we have inputs, we have output for training and testing, so we can build a machine learning model, right? Because if you want to train any machine learning model, we have to create input output pair, right? So this noise image is our input, and the clean image here is our output, right? So noisy images, comma clean image, right? So noisy image we will take as input, clean image we want in the output, right? Yes. So here we have created ground truth for the training data and the test data, right? Okay. If you want to upload any noisy images, then you can plot using this function, right? Now in this matrix format, we have arranged each input row wise, right? So for example, first row we have the first input, second row we are having second input, second image. Similarly, ith row we will get the ith image, right? So we have arranged input row wise in this matrix format, right? So if you want to display, let's say ith image, here we will pass ith index. So ith row will give us the ith image that we can visualize, right? Okay, I think I don't have code for this multi-output part. Yes. Okay, no problem. Yes. So here also we are using k-nearest classifier. So we will fit a k-nearest classifier to our data, right? So this x underscore train underscore mode is nothing but the input, noisy input, right? And this y underscore train underscore mode is nothing but the corresponding clean images, right? So when we pass these input outputs to this k-NN classifier, it will fit a model, and using this model we can make prediction, right? So for any given image, it will produce the clean image as an output, right? Any doubt here in this example?
How do we combine these various outputs, accuracy or precision?
Mhm.
Because you got multiple. Let's say you're training multiple models to evaluate, and then now you got a situation where, let's say, some model is predicting some of the outputs correctly, while some other model is predicting some other outputs correctly. So is there a mechanism to combine that output to say this model is performing better?
Yes, yes, good question. So, in fact, for all practical purposes, we generally use multiple performance matrices. So it's not like that we only rely on one performance matrix. In fact, we do rely on multiple matrices. So for the same problem, we will also calculate accuracy, we will calculate precision, we will calculate recall, we will calculate F1 score, right? And don't think we only have only these performance metrics. Depending upon our problem. So, for example, for classification, you can calculate accuracy, you can calculate precision, recall, F1 score, right? But let's say if you are doing a segmentation problem where you are assigning a particular value for each pixel. So segmentation is another problem. Detection is another problem, right? Classification is another problem. So for detection, or let's say for segmentation, we have some other performance metrics. So for example, intersection over union, right? So we are having several performance metrics, and we do combine these metrics, and then we will decide the best performing model, right?
So my question is, because you are getting multiple outputs, right? Earlier we were getting a single output. So we are able to evaluate that this model is performing better because we compare with the output, single output. Now it is possible in this case because you have got 784 outputs. So one model, let's say, is able to predict some number correctly, while some others are able to predict some other numbers correctly. So then how do we decide which model is the best?
Okay, so for this problem, what we can create, since we already have the clean images, and we have the clean images produced by this model KNN classifier. So what we can do, we can simply create Euclidean distances or distances between the actual output and the model predicted output, right? So if that distance is less, which means model is doing good, right? Because in output, what we are getting values from 0 to 255. So for each output we will have value from 0 to 255. So let's say if this model is not working fine, let's say if this model is not able to remove the noise present in the data, then we will have there some other values, right? So let's say this value, this example. Here, ideally, it should remove this noise, right? So this pixel value will get changed, right? So now we have this image that is produced by the model, and we have the actual clean image. So what we can do, we can simply take the difference or take the distance between the model predicted output image, model produced output image, and the actual output image. And what we want here, we want that number to be as small as possible, right?
If you were to take this same point to, let's say, regression problems, like you said, it has to predict height and weight. So in that case, how will we combine the output values to say that this model is better? Because some model may be predicting height better.
Yes.
Some may be predicting weight
So
better.
for regression, we will take RMSE error, root mean square error, or absolute error we will have. So whichever model is giving us the lowest error, we will pick that model,
So
right?
we'll take average of RMS here for those 784 or whatever the number of outputs which are there in that case.
Yes, sir. So in fact, RMSE is the root mean square error. So we will do the averaging there, right?
Okay, so you're saying for every output, we'll take an average.
Yes.
Is there any other mechanism to combine them? Or is it just the average?
No. In fact, we can have several other metrics. So absolute error we can take, a mean error we can take, right? And so mean and absolute are not the only ones, right? So
Sorry.
yeah, so
My
there are
question is, we have got multiple RMSEs now because there are multiple outputs. So how do we combine those multiple RMSEs?
No. We will not get. So for this problem or height and weight example.
Let's say you got multiple outputs, height, weight, and let's say there are some other values to be predicted. And then you, for each of those, because you have got multiple output features, you
Yes,
will
yes,
have
yes. So let's say in output we are having k output, right? So O1, O2 up to OK. Yes. O1, O2 up to OK. Right. So we will have model predictions. So assume this is the model prediction and this is the ground truth values, right? So ground truth value, I'm assuming G1, G2 up to GK, right? Now you will choose one metric. So for example, let's say the square is your metric. So first you will calculate this difference O1 minus G1 square plus O2 minus G2 square and so on. OK minus GK square, and then you will do this averaging because there are total K outputs. So here you will write K. Now this is the mean squared error. If you want to calculate root mean square error, you will do the root mean square operation. So this value we want as low as possible, right?
Okay. Are you going to cover this example also, multi-output for regression problems?
Yes. So nothing special in multi-output, same as the single output. The only difference is here, since we have the multiple outputs, so therefore we will here multiple outputs, right?
So in this classification problem, we will be using recall, precision, and these things, or root mean square will also we can also use.
No, it depends on the problem, right? So for classification task, we are having accuracies, right? Precision, recalls, and for regression, we have some other matrices.
Okay, so root mean square will not be using in classification problems.
No, it can be used in combination of accuracy.
Okay.
If let's say if your classes uh, suppose you are predicting some number, because it's not like that we have classification task, we have regression task. It may also possible that for the same problem we are doing both classification and regression, right?
Okay.
And one more thing, here this is only one way, right? I'm not saying this is the only way to get evaluate the performance of any multi-output model. So in fact, here what you can do, you can remove this square root, right? You can do this simple averaging, right? But yes, uh, directly you cannot add these numbers, right? O1 minus G1, because in that case some error will get cancelled out, positive negative error will get cancelled out. So for that reason, either we will use squared term or we will use absolute term, right? Yes. So yes, so remaining slide, I think in nothing special is there. So I have already covered all these topics. Yes.
Oh, one more thing. Uh, in the CloudX portal, there is some question related to OVO and OVA. Can you explain upon that?
Yeah, so one versus all and one versus that will be covered later.
Okay.
So what OVA is nothing but the technique using which we can use multiple binary classifier to solve a multi-class classification problem, right? I think I have already shared Jupyter notebook file and the PPT, but let me share it again.
Dr.
Okay.
Pravendra,
Yes, yes.
so we talked about KNN, SGD, random forest, all these decision trees, everything, right?
Mhm.
But it is that we are just using it from the ScikitLearn library. Will
Mhm.
you be covering the mathematical aspects
Yes, yes. So
of
support vector
those?
machine and these models I will cover. Okay, so it is given in the Jupyter notebook. So what happened in multi-class classification problem? Uh, one way here to solve multi-class classification is we can use multiple binary classifier. We can use multiple binary classifier to solve multi-class classification problem, or directly we can use models for multi-class classification problem. So here what we can do, we can create, we can use multiple binary classifier, right? So for example, for one versus all, what it method assumes. So assume this portion is one class and all remaining part is the another class, right? So it will create it will learn three binary classifier to solve this multi-class classification problem, right? So that strategy is called one versus all, because here we are creating multiple binary classifier to solve this multi class, right? I think multi-class classification is not there in these slides. Okay. Okay, so I will share some more slides to cover this topic, right? Binary classification and multi-class classification problem. Okay, so let's take a 5-minute break and then I will start another topic, training models, right? Okay, so for that also I'm sharing slides and Jupyter notebook file, training models, right? Yes, so please download training model PPT and training corresponding Jupyter notebook file.
Sorry, did you
Okay, so
share it in the chat?
yes, yes, I'm sharing. It is still
Okay.
uploading. So file is big. Okay, so let's take a 5-minute break and yes, so Jupyter notebook has been uploaded, so you can download that. Yes, both files. Done.
Also, for the next exam, which is
Mhm,
scheduled number 10, so it is saying that it's a linear regression. So,
mhm,
for that linear regression, what all topics that we have to cover actually?
mhm.
That is the one, just training model that
Yes,
you
so in
have
training
to.
model, I will cover linear regression part, right? So
Oh,
classification I have covered. Now I will cover regression part.
okay.
So the quiz which is there on 10th November or
Mhm,
11th November. So
mhm.
that will be based on this training model.
Yes, yes.
Okay.
Okay, so let's take a 5-minute break and then I will continue. Hello, am I audible?
Yes.
Okay, so let's start. Yes, so I have shared Jupyter Notebook file and the PDF file for training models. Yes, so let me quickly show you how nearest neighbor will work. So suppose if we are using one nearest neighbor means we will only consider first nearest neighbor, right? So let's say for this test point, this particular point is the first nearest neighbor, right? Now the prediction or the output will depends on nearest neighbor, and in this case, since we are using one nearest neighbor, so therefore we are only relying this particular training data, this particular training, uh, this particular nearest neighbor, right? Okay. So since in this case the class of this point is red, because here we are assume we are doing binary classification. We are solving here a binary classification problem, and we are only having two classes, red versus green class, and we want to predict the correct class for this particular test point. So the class for this test point can be red or can be green, and to decide that we are using here one nearest neighbor, right? So since the nearest neighbor class is red, so therefore we will predict its class red. And for this point again, we will use first nearest neighbor. We will only consider one nearest neighbor, and we will predict its class as green because this is the nearest neighbor, right? So this is how the nearest neighbor will work. And in case of nearest neighbor, this is the decision boundary, right? Okay, so let's not talk about decision boundary because I have not covered that topic. And k nearest neighbor, what we will do, we will decide using k nearest neighbor. K can be any number. So, for example, let's say if k is equal to 1, we will only consider one nearest neighbor. If k is equal to 3, then we will consider three nearest neighbor, right? So, in case of three nearest neighbor, we will consider three nearest neighbor: first nearest neighbor, second, and third nearest neighbor. And now we will decide its class. So again, here we can use several rules to decide its class. Either we can use averaging, we can use majority. So if you are doing majority, then in majority we are having green points, so its class will be green, right? So we can decide its class using majority rule, or we can decide using averaging also we can do, right? And we can also use the fact that since this point is more closer, so therefore we should give more weightage to this point and less weightage to these points. So that type of scheme we can also implement in practice, right? So there are several but by default it will do the voting, right? For the classification, it will predict its class uh, using voting scheme. So let's say if majority class is green, then it will predict its class as green, right? Yes. And the multi-class classification problem I have already discussed. In multi-class, we are having multiple classes, and input can belongs to exactly one of k classes, right? Not more, not less, exactly one class it will belong, right? And for multi-class classification problem, directly we can create a classifier where we can predict one out of multi-classes, one out of multiple classes, or what we can do, we can use multiple binary classifier to solve a multi-class classification problem, right? So if we are using multiple binary classifier to solve a multi-class classification problem, that method is called one versus rest or one versus all method, right? So let's say if you want to solve this three class classification problem, because here we are having three classes: first class, second class, and the third class. So what we will do, we will create, we will use here three binary classifier. One binary classifier we will consider red versus rest, red versus blue green combined. The another binary classifier we will use to classify blue versus rest, blue versus green and red, right? The third binary classifier we will use here green versus uh, red and blue combined, right? So these three classifier we will use here, these three binary classifier we will use to solve this multi-class classification problem, right? Okay, so let's take this example. Here we are having three classes, red class, green class and blue class. So this three class classification problem or this multi-class classification problem we will solve using multiple binary classifier. So we will use here one binary classifier, right? So this first class we will treat as a one class, and all other remaining classes we will treat as a this other class, right? Okay, so we will create one classifier where this is our one class, and all remaining classes we will combinedly collectively take as a second class, right? So here by using this classifier we can decide whether input belongs to this class or the remaining class, right? The second classifier we will construct separate to separate this particular class. So again we will use the same process, one class versus all other remaining classes. And for that binary classification task we will learn another classifier. Then we will learn third classifier. uh, so since here we are having three classes, so therefore we will learn three binary classifier, right? So for these three classes, we will learn three binary classifier. First binary classifier, second binary classifier, and third binary classifier. And after learning these three classifier, we can solve this multi-class classification problem, right? Okay, so how can we solve this multi-class classification problem using these three classifier? So what we will do, we will first use this first binary classifier, and we will make predictions using using first binary classifier. If this classifier is saying blue, which means its class is blue. If it's if this classifier is saying, let's say, prediction of this classifier is not blue, then we will use another model to decide that part, right? So here we will take predictions from all these models, and then finally we will predict its class, right?
Sorry, one quick question. Which slides are these?
So I think these slides are not given there. So maybe I can upload, if you want, I can upload these slides.
Yeah, that would be helpful because
Mhm.
uh, okay, yeah, that will be
But I
helpful.
think some more extra content is there in these slides. So what I can do, I can remove uh, n- uh, not relevant part, and then after processing these slides, I will upload, right?
So these are not the training model slides that you
No, no,
shared
no,
a
no.
few
Training
minutes
model,
back.
I'm not started. I was explaining this part. Binary classification versus how we can solve multi-class classification problem using several binary classifiers. So this part I was explaining, right? These methods.
Yeah, I mean, if you want, you can share the slide as they are and just say slide numbers. So we'll just do it that way if you want.
Oh,
I mean,
okay,
that will
okay.
save time.
Mhm. Okay, so I think this slide is not required. Actually, some topics I have not covered. So, for example, this large margin classifier I have not covered, right? Decision boundaries I have not covered. But yes, you can neglect these parts. Here you can only focus one versus rest, or this multi-class classification problem and the k nearest neighbor method, right? Okay, so I'm uploading this slide as it is, and
Can you upload the training models PPT as well? We have shared the PDF.
yes, yes. So I have already shared the PDF.
Can you upload the PPT? Because PPTs are easier to
No, no,
understand.
but I think in PPT content is different. So I will use this PDF file. But if you want, I can also upload the PPT. But in PPT, I think some topics are missing. Yes. So yes, you can download, right? Okay. So now let's start training model. So we have covered how can we train any machine learning model. So we can divide our data in two parts, and then we can train a machine learning model, right? We can choose the if we have multiple options, we can choose the best performing model depending upon some performance metrics, right? So for that we can use recall, we can use precision, we can use F1 score, we can use accuracy, or some other metrics we can use, right? Then we have different types of model. Using cross validation, we can select the best performing model. We can if there is some hyperparameter in that model, we can tune those hyperparameters also using cross validation, right? So now in this session, we will see how we are training these models, right? So for training, we will use training algorithm, right? So here,
One quick question I have. I
yes,
think
yes.
you mentioned earlier that you could use classification as well as regression.
Mhm.
When do we need to use them together
No,
for
let's
solving the
say
same problem?
yes, yes. So sometimes what happens, you are solving a complicated problem, a big problem you are solving. So one sub problem is a regression part, and one sub problem is a classification part, right?
Okay.
And in fact, it is also possible that for the same problem we are having different types of classification and different types of regression, right? Say, so for example, single output regression, multi output regression, right? Similarly, the multi-class classification problem, binary classification, so it is also possible.
Okay.
Yes. So here, for training these models, we will use gradient descent approach, right? So gradient descent is an iterative approach. So we will use several iterations to train any machine learning model, right? So in gradient descent, we will cover several variants of gradient descent, batch gradient descent, stochastic gradient descent, mini batch gradient descent. So all these versions of gradient descent, so we will use to train a machine learning model, right? Okay, and then we will see several ways of regularizing linear models. So we do regularize linear models to prevent overfitting, right? So and regularization is one method of preventing overfitting, right? So in regularizing linear models, we will see ridge regression, lasso regression, right? So these regression we will see. Then we will see logistic regression, right? And then we will see how we can use these concepts in building and training neural networks, right? I think I have already shared the slides, right? PDF file for training machine learning model part, right?
Yes.
Yeah. Okay, so let's discuss some notations, and I think I have already covered notations, but let's quickly go through this part. So yes, so this example I have already discussed, right? So here we are predicting a housing price given some input values, right? So inputs are given, and our goal is to predict the housing price, median housing value for a given district, right? Okay. And yes, so here also, let's say for this housing market, let's say if you are predicting housing market outcome, right? So there we can have a situation where we are doing both classification and regression task, right? So let's say you are predicting housing market outcomes, right? So the classification task can be, let's say, whether that house is we are having on high demand or low demand, right? Location, safety, types of property, what type of property we are having, right? So these types of problems we can have for one big problem, right? So these all are the classification tasks that we can do to solve a predicting housing market outcomes, right? Now for the same problem, regression task can be, let's say we are predicting housing price, right? Or let's say we are predicting number of bedrooms, or let's say we are predicting market trend, right? So these can be the associated regression task, right? Or let's take another example. Let's say if you are building uh, a software, or let's say machine learning model to assess health risk, right? For any insurance company, you are building a machine learning model to assess uh, the health risk, right? Now, for assessing health risk, we can have several classification tasks, several regression tasks, right? So here the regression will be, you want to estimate healthcare cost, or let's say medical expenses you want to predict over a specific time of period, right? So these are the regression tasks that we can do. And the classification task can be, let's say, you want to classify patient or the person into categories. So, for example, based on their income, right? Low, medium, high, or based on their lifestyle, you can categorize person into different categories. Based on family history, you can categorize in different categories, right? So in this case, we can have several classification tasks, several regression tasks for the same problem, right? So it can be possible where we are having uh, both classification and regressions, right? And in fact, in classification, we can have binary classification. Some tasks are binary, some subtasks are multi-output, some subtasks are multi-class classification. So this case is also possible, right? Okay. So here I've already discussed this example where we are predicting housing price given these inputs, right? Okay. So here small m uh, we small m's we generally represent the number of training number of training points in our data set. So for example, let's say if we have 20,000 district or 20,000 blob in our training data set, then in this case, small m will be 2000. So small m is nothing but the number of training data points, right? Xi, x superscript I, we will use to show that to show it is the ith instance or ith data point in the data set, ith training data in the data set, right? And the corresponding label, corresponding output, we will show by yi, right? Now xi is a vector, right? Because if let's say if in our input, if we are having let's say 5 feature, then the dimension of this this input vector will be a 5-dimensional vector, right? Because here now we have a 5 features, right? Okay. So this yi is the output label, and xi is the input for the ith training data point, right? Because in our data set we are having a small m number of training data point, and xi is the ith data point, and corresponding output we will represent by yi, right? And if we are having let's say 5 feature in our data, then xi is a vector of 5 dimension, right? Because we are having 5 feature in each data point, right? Okay.
Do we say xi is a vector or do we say x is a vector?
No, capital X is a matrix, right? Because here we will use capital X to show that it is a matrix where in each row we are having data points. So for example, first row is the first data point, second row is the second data point, third row is the third data points, right? So likewise, if we are having a small m number of data points, there will be a small m number of rows. And now how many columns we will have? Columns will be the number of features, right? So suppose if there are 100 feature in our data set, so there will be 100 columns, right? So capital X is a matrix which represent the complete data set, complete training data set, right? Now in this matrix X, we are selecting ith row. We are selecting ith row. So that ith row here is the xi. And the corresponding output here is yi, right? Because x we will use for input, y we will use for output, right? So this capital X is a complete matrix, complete data set, where row represent the data point and column represent the feature, right? So if there are 100 feature in each data point, there will be 100 columns. And if there are a small m number of training data points, there will be a small number of rows, right? Now we are interested in ith row, ith data point. So this ith row or ith data point is this xi, right? And the corresponding output is y.
So this y can also have multiple outputs, right?
Yes, if we are solving a multi-output problem. But if we have the single value in output, then yi will be a scalar, right?
Right.
Yes. Okay, so let's take this example. Here, let's say if we are interested in predicting median house value, right? Median house price we want to predict. So in this case, this value, median house value is our output, and longitude, latitude, and all these are nothing but the inputs, right? So in this case, this x1, because assume this is our first data points, so corresponding output will be this value. Median house value will be the output, and latitude, longitude, and all these values will be inputs, right? So how many features we are using for inputs? 4 features we are using, right? First feature, second feature, third feature, and fourth feature, right? So the dimension of this input vector will be here 4 cross 1, because there are 4 features in each input and one output we are predicting, right? So input is a vector and output is a scalar in this case, because we are only having one input. But if we are solving a multi-output problem, then output will be a vector in that case, right? Okay. This capital X is I already discussed. So capital X is a matrix that contains the complete data set, the all training examples. If we store where row wise, we are storing training data points row wise, right? So in capital X matrix, each row is a data point. Each row is a data point. So first example is the first row, second example second row, right? And column represents the number of features. Xi means the ith training example, right? Yes. So since we are having row wise, we have arranged data points row wise. So if you want to convert, if you want to write in column wise, so you can do the transpose operations, right? So here I am writing in transpose notation, because I want to represent these in column wise, right? So if xi is a row, if you perform transpose, it will become the column, right? Okay. Small h we are using here to show that. Um, so small h is also called the hypothesis, and small h is the machine learning model that we are training, right? So small h is a model, right? And using this model, we will make predictions, right? So we will pass input to this model, and this model will produce corresponding output, right? So the model output here we are representing by y hat. So y hat means the output produced by this model, right? So this model H will take input and produce output, right? Now the actual output we are representing by yi, right? So yi is the actual output, xi is the ith input, yi is the ith output, and the model predictions here we are representing by yi hat. So yi hat means the output predicted by model, right? Now we are having two values, model predictions and the actual value. So we can we can calculate errors, right? So for example, if you are predicting housing price, so we have the actual house price, and we have the model predicted house price. So since now we have these two values, we can take this difference and we can calculate the error, right? And accordingly we will choose error matrix. So we can choose root mean square error, we can choose mean square error, we can choose absolute error, right? So we have different types of error matrix, and we will choose depending upon our requirement, we will choose one metric, right? So here, this RMAC, root mean square error or mean square error or absolute error is nothing but the cost function, using which we are calculating, we are checking how good our model is doing, right? If model is predicting correctly, which means this error should be small. If error is large, which means model is not doing good, right? So using this cost functions, we can check how good our model is doing, right? Okay. So lowercase in italic font we will use to denote scalar values. right? So for example, yi is nothing but the ith actual output, right? Ith actual output, which is a scalar, right? If we are predicting single output, it is a scalar. If you are doing multi output, then it will be vector, right? Okay. Lowercase, if I'm writing anything in the lowercase bold font, which represents the vector. So for example, this xi is a vector, and here by default we will assume column vector, right? So whenever I say vector, vector means column vector. If I want row vector, what I will do, I will calculate transpose. So transpose of column vector, I will get the row vector, right? Uppercase font we will use here for matrices. So for example, this uppercase bold font capital X means X is a matrix. Lowercase bold font means it is a vector. Lowercase italic font or lowercase font means uh, the symbol that we are using here for the scalar values, right? So for example, M is a scalar, this is a vector, this capital X is a matrix, right?
In case of multi-output, do
Mm.
we still use capital small y, right?
No, 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 no. We will
Although
use
it will be a
lowercase bold
matrix.
font. Yes, lowercase bold font we will use then. We will here use yi in a lowercase bold font, because in multi-output it is a vector, right?
So it can be matrix also, right? If there are multiple outputs, multiple values.
Yes, it can be, because let's say uh, for the same input, if you are predicting multiple things, right? So uh, let's say if you are doing if you are predicting multiple things, right? So let's say one output is uh, regression, one output is, let's say, classification. It can also happen, right? So in that case, you can even have this type of output, right? But mostly what generally we do, if we have one big problem, we generally divide that big problem into a small sub problem, and then we will individually solve that sub problem, right? So let's say if we have one big problem where we are having uh, regression problem, classification problem, so we will solve individually solve classification problem, we will individually solve a regression problem. And sometimes what we will do, we will use common features or common pre-processed input to solve these problems, right?
Yeah, but the notation remains small y, right, for output, regardless of whether
Yes, yes, yes. So notation will remain the same if we are using uppercase bold font, which means matrix, lowercase bold font means vector, and lowercase means it is a scalar, right? Okay, so next session I will start linear regression, where we will see how can we train linear regression model. So again, in linear regression, what exactly we are doing? We are learning a linear model, right? So here linear means we are learning a linear model, and regression means we are predicting a real valued output. So given input, we are predicting a real valued output. Now this regression can be can have a single feature, can have multiple features, right? So if you are so what I mean by single feature, so for example, life satisfaction. So you can calculate, you can estimate life satisfaction given GDP per capita. So here to calculate this output, we are only using one input, right? Or one features. But in regression, it may also possible that using 10 inputs, we are predicting one output, right? So for example, this housing prediction price. So this one output we are predicting using several inputs, right? Or several features we are using to predict one output. And this regression can also be linear, can also be non-linear, right? So linear means we are learning a linear model. So depending upon how many inputs we are using, this model will change. So for example, if we are predicting output given one input, then in that case, this linear model will be a line, right? But let's say if you use two input and you are predicting one output, so assume X, Y, and Z. So Z is output and X, Y are the input. So in that case, what we are learning? Plane, a plane we are learning. If we are having more than two inputs, then we are learning a hyperplane. So in linear regression, either we will learn one line, or we will learn plane, or we will learn hyperplane, right? Okay, so I will start linear regression in the next session, right?
Okay, thanks.